Hello everyone, welcome back to our Introduction to CFD course. This time around I'm gonna teach you some not so basic but some data analysis options, data analysis tools that you can use to get information from the simulation that we have just did. Okay, so you go to your simulation. It can be the transient with decay or the transient without decay. It will be the same for both. So you open the results for it, and what we're gonna do is that we're going to extract some data from this simulation. Okay, so what you will do is first you're going to create this expression right here. All right, so if you don't remember, or to create an expression, all you need to do is go to insert expression, but I have this expression already created. Okay, we're actually going to create two expressions. The first expression is going to be called the velocity normal, right? It's going to be the velocity that is normal to the outlet face right here. It's going to be the velocity that is normal to this face. Okay, you cannot use the velocities that are already in the software because they are not normal to this face, because this face is in the diagonal. All right, so what we're going to create is going to be this expression that I named v normal. All right, and it's going to be the velocity normal u times the normal vector x plus the velocity v times the normal vector y plus the velocity w times the normal vector z. So it's basically the normal velocity in all the directions. Okay, and I named it v normal. All of these variables here can be found inside the ANSYS library, or you can just type it. You can type it velocity u the way it's typed here with the v in major case, or you can go to functions and then you go to variables, and you can find already here the velocities, right? U, v, and w, and you can already find the normal vectors as well. Okay, so you can do variables, velocity u, then asterisks because it's the nomenclature for multiplication, and then you insert the normal x, and then you repeat it for all the other components. But you can also do this by typing. All right, it will work the same way. And now the other expression that we're going to create is the one that I called tracer mass. What this expression is basically doing is that is getting the tracer mass at the outlet, and is getting the tracer mass in the units of kilograms per second. All right, it's not getting the tracer in its concentration units. It's already giving us the mass flow rate at the outlet. All right, which is something that is extremely useful for us. All right, because we can see and know the tracer mass flow rate at every time step during this process. Okay, so how this expression is created? We're going to create the area int times open parentheses tracer, which is the variable that we created. This is our additional variable, times the v normal, which is the expression that I have just showed you guys, the velocity normal to the outlet face at the outlet face. All right, the same thing can be done here. If you go to function cell, you can find, actually not function cell, you go to not location, you go to functions, and then you go to CFD post, and you can find the area int right here. Okay, so it will be area int, let me give a little bit of space just to show you how it's done. Area int, and then you go inside the parentheses, you go to variables, tracer, asterisks, then left mouse again, right mouse again, expressions, you go to other, and you look for the v-normal expression right here, over there. Then you go to after the at, location, outlet. So this is how you would create this expression, all right? Very straightforward, right? So after you created this expression, you're going to create a chart. You can name the chart anything that you want, and then you're gonna go here to XY transient or sequence, because we're getting our information from a transient simulation, from a transient sequence, right? Then you can leave the name as series 1, that's no problem. You change location to expression, okay? And then you're gonna look for the expression that we just created. In my case, I named it tracer mass, right? And then you go to the X file and the Y file and make sure that the X file is time and the the X axis is at time and the Y axis is at tracer. Okay? And all you need to do is you need to apply. And this is going to take a little bit of time because it's going to go look for every single time step and is going to extract this information from every single time step. Okay, so at the end you have a chart right here that is tracer times across the time. All right, and what you will do after this is done, a bar will appear here that is going to show you the progress of this chart. After this is done, you can just export the file to whatever folder that you want, and you're gonna have it at CSV file. All right, I believe we have done this in a previous lecture. I showed you guys how this is done and how to extract the file, but I'm showing you again just as a refresher, right? So what we're gonna do with this file, we're going to create an Excel spreadsheet, all right? The first thing that you're gonna do is going to insert all of these values. They're gonna be the same ones for you as they are for me, okay? Because the simulation is the same, okay? So you have the inlet velocity, the inlet area, the inlet flow rate, the tracer concentration, the injection time, and the tracer mass at the end, okay? Which is right here. This is an information too. This is an information. This is an expression, which is just the tracer area times the velocity. All right, we get the tracer flow. This is an information. This is an information, and the tracer mass is just the inlet flow rate times the concentration times the velocity inflow. Okay, so is I9 is tracer concentration, I10 is injection time, and I8 is the inlet flow rate. We get the tracer mass right here. Okay, and to continue this analysis, we're gonna put the information that we extract from the simulation. They are these two columns right here. Okay, they are, you can see that the first one is time, like we put in the x-axis, and in the y-axis is the tracer mass that comes from the expression. As you can see, the unit here is kilograms over second, which means it's mass over time. So this is the mass flow rate that comes from this expression right here. You can see the units for this expression here. All right, so you're gonna put this information in these first two columns right here, and what you're gonna do here is basically an integer, all right? It's basically the sum of these two terms times the subtraction of these two terms. So it's B7 plus B6 times A7 minus A6, and all of this is divided by 2, and this is repeated in every single other line right here up until the last one. You can see the last one is B1337 plus B1336 times A1337 minus A1336. These values are going to be different from mine folder here to yours because the time steps that I chose are different. Is different. Okay, so don't be worried if yours is a little bit less or more than this 1337. All right, this is perfectly normal. So these expressions start in the second line after the data, right? Because the first line is going to be the sum of this column. Okay, so this line right here is basically the sum of all the values here. Okay, this you don't need. This is just for my analysis, for my problems, but you will need this one. This is basically the how much cumulative mass is leaving the outlet, all right? So we want this value here to be 95, which is basically 95% of mass has left the domain by this time. And how we get to this value is basically governed by this sum and the tracer mass right here. Okay, this value is the same as this one, all right? So it's basically 100 times, because I want in percentage, 100 times the sum divided by the tracer mass. Okay, and how we know this value right here? We want this value to be 95. So for example, let's say that I'm going to put all of the 137 values here. So I'm gonna put 1337. Okay, see that it has gone up to 96%. I don't want 96%, I want 95%. Okay, so let's say that I put here 1000. It goes down to 89. So all you need to do is find the value that reaches 95%. In my case, it's 1290, but like I said, the amount of data that you have is going to be different from mine. So we are going to have to find the value that gives you 95%. Okay? And this is done for the transient without decay. Okay? So for the transient with decay, is going to be the same thing. You can even like copy this whole lines and columns, this whole data here. You can just Ctrl+C, Ctrl+V somewhere else, and you will put the data for the transient simulation with decay in these two columns. Okay, and this will yield you the result that you want from this column right here. The only thing that you need to do that is additional is this line right here. This line is gonna be the 95% mass that has left the simulation minus this value right here, which is the same, which is given by the same thing that is given here, but of course the sum is from the data for the transient simulation with decay. Okay, and divided by the same tracer mass. And this subtraction gives you the amount of mass that was removed by decay. So this basically is going to give you the how much the vegetation has removed mass from this simulation. Okay? And this is the value that you want by the end. You want to see, okay, how much mass this vegetation arrangement is removing from our system. Okay? And the last thing that I want you guys to do is to create graphs from this. Okay, so let's create a scatter graph. Let's put it something like this with this arrangement, and now let's select the data. Okay, so the first one, I'm gonna name it tracer no decay, and it's gonna be this one, this data right here. So the time and the mass flow rate. There you go. I'm gonna make this a little bit prettier by moving you here. I don't need this title. I'm gonna increase the size of my graph. Here we have the time in seconds, and here we have the tracer mass flow rate, which is given in kilograms per second. Okay, and I'm gonna increase this. Don't need to increase this. This size is fine. But we also want to see the other one. So we want to see the tracer with decay. Let's say, since I put yes decay, since I put no decay, I'm gonna put tracer yes decay. The x value is gonna be this one, and the y value is gonna be this one. All right. So you can see already that the spread of our curve makes complete sense, right? Because if I don't have for the blue curve, I only have tracer moving throughout our system. Nothing is removing it from the system inside of it. Okay, so all the tracer is gonna be able to reach the exit at some point in time. All right, the orange curve, however, we added a decay equation in our vegetation, inside our vegetation. So every tracer that reaches the vegetation is going to be removed following that rate. All right, so it's natural that we have a lower tracer curve throughout the whole curve, because this is due to the decay of the vegetation. So this is the influence of the vegetation right here. This lowered orange curve is due to the decay that is due to our vegetation, right? So you can clearly see just by looking at the graph that we're gonna have less tracer reaching the exit just by the insertion of our vegetation. So you can already tell just by looking at the graphic that by adding this vegetation, we get a lower amount of tracer, and because the tracer is our analog to pollution, we would have a better quality of water in a system with vegetation with the decay active. All right, so basically this is what I want you guys to do for me now. Extract the information from your simulation and do this analysis right here, which is basically something that you would do if you were using CFD to analyze a nature problem. All right, a problem for your master's degree or your PhD degree. Okay, if you have trouble generating this spreadsheet, let me know, then I can send you it, but I really would like you guys to try to do this on your own. All right, just ask for the spreadsheet if you really have trouble with doing it yourself, and even then I would ask you guys to use the spreadsheet as a reference, not just to go here and paste your results here and paste your results here and find the results. Okay, so Hope you guys understood this lecture. This would be the end game of our simulations right here, like the information that we can get from it, from our CFD simulation. All right. So hope you guys have a good time. Good luck, and any doubt that you have, you can send me via email. All right. Take care.